Silicon wafer the size of a dinner plate. Less than 1 millimeter thick. Inside it, up to 1,000 individual chips, each carrying billions of transistors etched at a scale smaller than most living cells. That wafer started as beach sand. Here is exactly how that transformation happens. Let's trace how 200 kilograms of raw silicon becomes a wafer holding 1,000 chips, each one containing up to 15 billion transistors, across a process that unfolds across several months inside the cleanest rooms on Earth. It starts with sand, not ordinary sand, but silica-rich quartz, with silicon dioxide content above 99%. That raw material enters an arc furnace running at temperatures above 1,600 Celsius, 2,112 Celsius, where carbon rods strip oxygen from the silica through a reduction reaction. The result? Metallurgical-grade silicon at roughly 99% purity. That sounds impressive, but for semiconductor manufacturing, 99% is nowhere near sufficient. Chips require silicon at 99.9999% purity, 9 nines, a grade called electronic-grade polysilicon. Achieving it requires a second chemical refining stage using trichlorosilane gas, distilled and decomposed at $1,100 per each inside sealed reactors. From electronic-grade polysilicon, the factory grows a single crystal. The method is called the Czochralski process, developed in 1916 by Polish chemist Jan Czochralski, and the semiconductor industry still uses it today, over a century later. Chunks of purified polysilicon are loaded into a quartz crucible and melted at 1,114 degrees Celsius, 2,572 degrees, the exact melting point of silicon. The furnace atmosphere is pure argon, an inert gas that prevents any oxidation. Then a seed crystal, a precisely cut silicon rod about 1 centimeter in diameter, is lowered until it barely contacts the melt surface. The seed is slowly rotated, typically between 10 and 20 revolutions per minute, while simultaneously being pulled upward at a rate of 1 to 2 millimeters per minute. As the seed rises, silicon atoms from the melt attach to it in perfect crystalline alignment, extending the lattice atom by atom. The result, after roughly 24 to 48 hours of continuous pulling, is a cylindrical single crystal ingot, 300 millimeters, about 12 inches in diameter, up to 2 meters, 6.5 feet long, and weighing approximately 200 kilograms, 440 LEBs. Every atom in that ingot is aligned in the same crystalline direction. That structural uniformity is not aesthetic. It is the physical foundation that allows transistors to switch reliably at speeds measured in gigahertz. Boron or phosphorus is added to the melt in precise, controlled amounts, typically a few parts per billion, to set the electrical properties of the silicon before the ingot is even sliced. The ingot is ground to an exact diameter of 300 millimeters, then sliced into wafers using diamond wire saws, running at speeds of up to 30 meters per second. Each wafer comes out between 775 and 925 micrometers thick. After slicing, both faces are lapped and chemically mechanically polished, a process called CMP, until surface roughness drops below 0.1 nanometers root mean square. That is less than the diameter of a single silicon atom in practical terms. Why does that level of flatness matter? Photolithography, the process that prints circuit patterns onto the wafer, operates with a depth of focus of roughly 100 nanometers. If the wafer surface deviates by more than 50 nanometers across the exposure field, the projected image blurs and the printed features lose dimensional accuracy. At 3 nanometer node manufacturing, a transistor gate is approximately 12 silicon atoms wide. A surface variation of even 30 nanometers would place that gate completely outside the focal plane. The batch, potentially 25 wafers carrying 25,000 chips, goes to scrap. Polishing tolerances are therefore enforced to within plus 0.2 nanometers across the full 300 mm surface. With polished wafers qualified, fabrication moves into the clean room, and the environment changes completely. Semiconductor clean rooms are classified by the number of particles larger than 0.1 micrometers per cubic meter of air. A standard hospital operating room runs at ISO Class 5, meaning fewer than 3,920 particles per cubic meter. Advanced chip fabrication areas operate at ISO Class 1, fewer than 10 particles per cubic meter. The air in these rooms is recirculated through HEPA and ULPA filters up to 600 times per hour. Temperature is held at 24 to plus 1 GDC. Relative humidity is controlled to 45%, plus 0.2%. Workers wear full-body laminar flow suits, called bunny suits, covering every surface of skin and hair, because a single human hair is approximately 70,000 nanometers wide, orders of magnitude larger than the features being printed. Inside the clean room, the wafer surface is first coated with a thin film of photoresist, a light-sensitive polymer, applied by spin coating at 3,000 revolutions per minute, producing a uniform layer between 30 and 100 nanometers thick. The wafer then enters the photolithography scanner. The scanner projects ultraviolet light through a patterned quartz mask called a reticle, reducing the image by a factor of 4 and focusing it onto the wafer surface. At the most advanced nodes, 3 nanometers and below, the light source is extreme ultraviolet, EUV, with a wavelength of just 13.5 nanometers, generated by firing a laser at a tin droplet 50,000 times per second, vaporizing it into plasma. Each EUV exposure takes approximately 10 milliseconds. A single wafer requires between 15 and 40 separate exposures, one per circuit layer, with each layer aligned to the previous, with an overlay accuracy of less than 2 nanometers. The machine performing these exposures is an EUV lithography scanner built by ASML, a Dutch company based in Veldhoven. Each unit weighs approximately 180,000 kilograms, roughly 400,000 lbs, stands 10 meters tall, contains more than 100,000 individual components, and requires 3 dedicated Boeing 747 cargo flights to deliver. A single EUV scanner costs approximately $380 million. ASML produces roughly 60 of these machines per year, and global chip demand currently exceeds that supply. The scanner's internal mirrors, which redirect the EUV light across the optical path, are the flattest large objects ever manufactured. If one of those mirrors were scaled to the size of Germany, the largest surface deviation would be less than 1 millimeter. There are currently fewer than 200 EUV scanners operating worldwide, concentrated in fabrication facilities in Taiwan, South Korea, and the Netherlands. After each lithography exposure, the wafer undergoes development. The exposed photoresist is dissolved away, leaving a pattern of open trenches in the resist layer. Those trenches define where the next process step will act on the silicon beneath. Etching removes material from the exposed areas. Dry etching, the dominant method at advanced nodes, uses plasma generated from gases such as fluorine or chlorine compounds at pressures between 1 and 100 millitorr. The plasma bombards the silicon surface with reactive ions, removing material with dimensional control down to 0.5 nanometers per etch cycle. A single transistor gate stack may require 12 to 15 separate etch steps, each targeting a different material layer. Deposition adds material. Chemical vapor deposition, CVD, and atomic layer deposition, ALD, grow thin films, oxides, nitrides, metals, with thickness control at the single atomic layer level. ALD works by alternating 2 gas phase precursors, each of which reacts with the surface in a self-limiting way. 1 atomic monolayer per cycle, typically 0.1 nanometers thick. A 5-nanometer gate oxide requires approximately 50 ALD cycles. Doping implants specific atoms, boron, phosphorus, arsenic, into the silicon to modify its electrical behavior locally. Ion implantation accelerates dopant atoms to energies between 1 keV and 1 meV and fires them into the wafer surface, embedding them at controlled depths between 10 and 200 nanometers. After implantation, the wafer is annealed at temperatures between 900 grams and 100 grams for fractions of a second using flash lamps, activating the dopants without allowing them to diffuse beyond their target positions. This full cycle, deposit, expose, develop, etch or implant, clean, repeats between 500 and 1,000 times across all layers of a modern chip. Total fabrication time for a leading-edge wafer, 12 to 16 weeks inside the fab, running 24 hours a day, 7 days a week. A facility like TSMC's Fab 18 in Tainan processes approximately 100,000 wafers per month. Copper interconnects, the wiring that links transistors into functional circuits, present a separate set of constraints. A modern chip contains between 12 and 18 metal wiring layers, stacked vertically and separated by insulating dielectric material. The total length of copper wiring inside a single chip, if unspooled, can exceed 10 kilometers, 6.2 miles, all within a die measuring roughly 5 by 5 millimeters. Copper is deposited using electrochemical plating. The wafer is immersed in a copper sulfate solution, and a current is applied, causing copper ions to deposit into pre-etched trenches. The process must fill trenches as narrow as 5 nanometers without leaving voids. A void 2 nanometers in diameter inside a copper line creates a resistance increase of more than 40%, which at gigahertz switching speeds translates to signal degradation and timing failure. After plating, a second CMP step removes excess copper from the surface, leaving it flat to within 3 nanometers across the full die area. Resistivity of the deposited copper must fall between 1.67 and 1.75 micro-ohm centimeters. The tolerance window is less than 5%. Variations outside that range alter propagation delay across the interconnect by up to 12%, causing the chip to fail timing verification at its rated clock frequency. The entire interconnect build, 15 layers of copper, 15 layers of dielectric, 15 CMP steps, adds another 6 to 8 weeks to the total fabrication timeline. When the last metal layer is complete, the wafer holds up to 1,000 individual dies. Each die on a leading-edge process node contains between 10 billion and 85 billion transistors. TSMC's 3-nanometer node packs approximately 292 million transistors per square millimeter. Apple's M2 Ultra chip, manufactured on that node, contains 134 billion transistors in a die roughly 90 square millimeters in area. To put that density in physical terms, if each transistor in a 15 billion transistor chip were scaled to the size of a grain of sand, 0.5 millimeters, the total volume of sand would fill a cube roughly 10 meters, 33 feet, on each side. All of that, compressed into a chip you can balance on your fingertip. The switching speed of each transistor is approximately 1 picosecond, 1 trillionth of a second. In the time it takes a human to blink, roughly 150 milliseconds, a single modern processor completes more than 150 billion switching operations. The global semiconductor industry produces approximately 1 trillion chips per year across all manufacturers and process nodes. That is roughly 125 chips for every human being on Earth, every year. The total capital investment required to build and equip a single leading-edge fabrication facility, what the industry calls a fab, currently exceeds $20 billion. TSMC, Samsung, and Intel are each investing between $40 and $100 billion in new fab capacity between 2024 and 2030. The first integrated circuit, built by Jack Kilby at Texas Instruments in 1958, contained a single transistor and a handful of resistors on a germanium substrate the size of a finger. 66 years later, the same basic principle, transistors switching on and off, now executes at a density 15 billion times greater. After fabrication, every die on the wafer undergoes electrical wafer sort testing. Automated probe stations lower arrays of tungsten needles, each 25 micrometers in diameter, onto the contact pads of each die simultaneously, applying test vectors that exercise every logic path, memory cell, and analog circuit. Testing runs at speeds up to 6 GHz and takes between 30 seconds and 3 minutes per die, depending on chip complexity. Dies that fail any test vector are ink-marked and excluded from further processing. Typical yield, the percentage of dies that pass all tests, ranges from 50% to 95%, depending on process maturity and die size. Larger dies have lower yields because a fixed number of random defects per unit area affects more of the chip's area. A 500 square millimeter die at 1 defect per square centimeter yields roughly 60%. Failed dies are not discarded entirely. They are analyzed by failure mode. Those with only minor defects are sometimes sold as lower specification variants with disabled cores or reduced cache, at prices 30 to 50% below the full spec part. Passing dies are singulated from the wafer using a diamond-tip dicing saw or a stealth laser that cleaves along crystal planes. Each die is then mounted into a package, a protective housing of molded epoxy with metal contacts in tin-silver alloy or gold. Advanced packages use flip-chip bonding, pressing the die face down onto a substrate with solder bumps as small as 40 micrometers in diameter, achieving interconnect densities of up to 2,500 connections per square centimeter. Packaged chips undergo final test at temperature extremes, typically 40 degrees Celsius to plus 125 degrees Celsius, to screen for latent defects. Units that pass ship in anti-static trays or tape-in-reel format to device manufacturers. A high-end processor retails between $300 and $700 US. The total market value of semiconductors shipped globally in 2024 exceeded 600 billion US dollars. From silica sand refined to 9 nines purity, through 12 to 16 weeks of fabrication, across up to 1,000 process steps, to a die holding 85 billion transistors, switching at 1 picosecond each. Semiconductor manufacturing is the most dimensionally precise industrial process operating at commercial scale today. One final number worth keeping. At leading-edge nodes, between 5% and 40% of all dies produced are downgraded or scrapped after months of processing, meaning that a significant fraction of every $20 billion fab's output never reaches a finished device. Which other manufacturing process would you like to see broken down at this level of detail? Drop your suggestion in the comments below, and subscribe to the channel so you never miss the next one.